This is chapter 3 for the AP Chem review on mass relationship and chemical reactions. First off, the average atomic mass is the first thing brought up, which is the mass of each element. Notice that the elements aren't whole numbers for the most part, which means it's not as simple as adding up the protons and neutrons like was described in the last chapter. For example, a unit measure is called an AMU, atomic mass unit. Some people refer to it as a Dalton, and it's 1/12 of a carbon-12 atom. So carbon-12 was the original standard for an AMU. The mass is an average of all the different isotopes times their percent abundance, and what we're going to do is give you a question right here to figure this out. It says two isotopes of boron, boron 10, which is 19.8% abundant, and boron 11, which is 80.2% abundant. Find the average atomic mass if the boron 10 is actually 10.0129 AMU, and the boron 11 is 11.0093 AMU. Now first off, in Chem 1, we didn't give you these values on the bottom. We just said boron 10 is a mass of 10, boron 11 is a mass of 11. Our book tries to get it exactly down to the correct AMU, so it is a little bit different. Calculation-wise, it's the same thing though. We're going to take the percent times the mass, the percent times the mass. So my first step is going to be taking 19.8, which is the percent, and I'm going to multiply it by the mass, which is 10.0129. I'm going to get that to equal value. Then I'm going to take the percent of 80.2, and multiply it by its mass, 11.0093. When I do that, I end up getting 198.255 and 882.946. If you add these two values, divide by 100 to undo the fact that this was a percentage and not a decimal, you would end up with 10.8 AMU as your answer. I stick with 3 digits because both percentages were given 3 sig digs as well. So last thing I note on this slide is that yes, this is a little different than what we covered in Chem 1, but the same idea of mass times percent, add them up, divide by 100 is the same. The only difference is our textbook, and I'm uncertain if the AP test will do this or not, but it gives it to you in the exact AMU measurement instead. Avogadro's number is 6.022 times 10 to the 23rd. This is another one where in Chem 1 we just said it was 6.02 times 10 to the 23rd. This is how many molecules or atoms or ions are in 1 mole. The molar mass is how many grams are in 1 mole. You use your periodic table to figure that out. An example of carbon dioxide has a molar mass of 44.01 grams per mole. The reason why we can say that is if you look on the periodic table, carbon has a mass of 12.01. Oxygen is 15.9994 or 16. So 2 of the 16s is 32, plus the 12.01 gets you to the 44.01 grams per mole, which once again is referred to as the molar mass. The conversions between the two I talked about in Chem 1 and in Chem 2 as well. If you start with a mass in the grams and you wanted to go to moles, your conversion would have 1 mole on the top and the grams per mole, the molar mass, on the bottom. Going from moles to atoms would be Avogadro's number on the top over 1 mole. On the other hand, if I started with atoms and I went to moles, this is when I want 1 mole on the top, Avogadro's number on the bottom. Remember when you have Avogadro's number on the bottom of a conversion, that you have to have all this in parentheses or use the EE button, or else it'll actually multiply by 10 to the 23rd when you need to divide. And then lastly, moles to grams would be the grams on the top, 1 mole on the bottom. Sample problem could be how many grams is 4.2 times 10 to the 22nd molecules of copper 1 carbonate. So what I'd first do is write down what I am given. 4.2 times 10 to the 22nd, this is molecules, copper 1 carbonate. I'd have to figure out the formula for that. So to start off with, the formula would be Cu2CO3. The reason why I figured that out is this is a -2 for carbonate polyatomic ion, +1 because it says copper 1. I'm actually running out of a little bit of room, so I'm going to start over here a little bit more. 4.2 times 10 to the 22nd. My first conversion is to get to moles. Because remember, if I start with atoms, I want to get to moles. That'd be 1 mole over Avogadro's number, 6.02 times 10 to the 23rd. If you're comfortable putting equals and then solving and then doing the second step, you can. I do both steps at once. Second step is grams. Well, look on the periodic table. The mass of 2 coppers, 1 carbon, and 3 oxygens is 187.2 grams in 1 mole. Divide by Avogadro's number, multiply by 187.2, and it'll get your correct answer. Keep in mind that sig digs are based off of measurements, not off of conversions. These are known values. So my final answer should only have 2 digits. I ended up with 13 grams of Cu2 CO3. You will have to know the reverse conversion as well, but that's the first one that we have to be able to do. Percent composition is the next calculation that the book goes over. Percent composition is the number of atoms, the molar mass of each element, divided by the molar mass of the compound times 100. Example would be, what's the percent composition of each element in sulfuric acid? Well, sulfuric acid was a question we went over in the last chapter. The formula for sulfuric acid is H2SO4. So what I want to do is figure out what percent of H2SO4 is hydrogen, sulfur, and oxygen. Hydrogen's mass is 1.01, and I have 2 of them. So the mass due to hydrogen is 2.02. Sulfur has a mass of 32.07, and there's only 1 of them, so 32.07. Oxygen has a mass of 16 times 4. It's going to give me 64. If I add up all of these, that'll tell me the total molar mass, which I have is 98.09. Now what I would do is, I would start over again. Hydrogen equals 2.02, its mass, divided by the total, 98.09. Sulfur equals 32.07 over 98.09. Oxygen equals 64 divided by 98.09. Divide the 2, multiply by 100 to express it as a percent, and I end up with 2.06% for the hydrogen, 32.69% for the sulfur, and 65.25% for the oxygen. And hopefully they get close to adding up to 100%, if not exactly on 100%. So that was a percent composition problem. Percent composition is something we covered in Chem 1. The exact opposite of percent composition is empirical formula. Empirical formula is determining the simplest whole number ratio of elements within a compound. The molecular formula can be determined by the empirical formula and knowing the approximate molar mass of the compound. Now this last part, approximate mass of the molar compound, is something that we added on from Chem 1. So again, something we didn't cover in Chem 2, but if you remember Chem 1 empirical formula, this isn't that big of a step. Here's a sample problem. A sample of a compound containing boron and hydrogen contains 6.444 grams of boron and 1.803 grams of hydrogen. The overall molar mass of the compound is around 30 grams. What is the formula? We cannot compare grams to grams directly. So what we have to do is first convert to moles. So if I start with 6.444 grams of boron, I'm going to convert that to moles. 1 mole over 10.81 grams. I'm going to do the same thing for my hydrogen. Hydrogen gives me 1.803 grams. 1 mole over 1.01 grams. We cannot compare grams directly from one atom to another because grams are different depending upon the atoms. Some atoms are larger than others. But moles we can compare from one another. I get 0.596 for my moles here, and I get 1.785 for my moles here. This is not a simple whole number ratio. So the next step we would do is divide by the smaller number of moles, in this case by 0.596. If I do that, my boron moles is now 1. My hydrogen moles is now going to be 3. So initially, that tells me the formula of this compound would be BH3. This is not the final answer in this particular problem. In Chem 1, this is where we would stop. This second line is what we have to take account for now. The molar mass of the compound is about 30 grams. The molar mass of this compound is around 13 grams. 10 and 3 more is 13. So that cannot be the case. So instead, if I multiply this by 2, I get B2H6. Now if I check boron being 10.81, hydrogen being 1.01, that gives me a total molar mass of 27.64 grams per mole. Is that about 30? Yes, it is. So this formula is actually B2H6. Once again, what we did is we converted our grams into moles. Then we divided by the smallest number of moles to get a whole number ratio. That was this step here. The second part of the problem, though, says that the molar mass is around 30 grams. So it couldn't have been this, because this is only around 13 grams. But by multiplying this by 2 to give me B2H6, that does give me my final answer there. Moving on. Well, last thing I guess to note here is instead of masses, we could give you percentages as well. If they do give you percentages within a problem, just treat it like grams. So if it was 42% of boron, then say 42 grams, and then 58% of hydrogen, 58 grams, and you can go from there. Chemical equation is the next thing we need to go over. Remember, on the left side of the arrow are reactants, on the right side of the arrow are products. We will use phase notations, an S for a solid, an L for a liquid, a G for a gas, and AQ being aqueous, which is a solution. Remember, you must balance your chemical equation. And the equation I'm going to write down for you right now is solid potassium chlorate decomposes into solid potassium chloride and oxygen gas. So, once again, chlorate means there's a polyatomic ion involved. Solid potassium chlorate, KClO3, with an S for solid. If it's a decomposition reaction, which we'll talk about more in a little bit, it means it's going to create potassium chloride, KCl, which is a solid, plus O2, which is a gas. Conservation of mass says however many atoms we start with, we have to end with. There's 1 K, there's 1 K. There's 1 Cl, there's 1 Cl. There's 3 oxygens, there's 2 oxygens. To make this work, I put a 2 in front of the KClO3. By doing that, I have 2 times 3 is 6 oxygens. Now I can put a 3 here, I have 6 oxygens. But I have to go back and rebalance my KCl, so there's 2 KCl. So to do balancing equations is the first step, which leads us into stoichiometry. Stoichiometry is called the quantitative study of reactants and products in a chemical reaction. Give you an example, nitrogen and hydrogen gas synthesize to make ammonia, which ammonia might be referred to as nitrogen trihydride. So nitrogen gas, nitrogen being a diatomic is N2, plus hydrogen gas, H2, makes NH3, which once again is a gas. First thing within stoichiometry is balance the equation. I have 2 nitrogens, let's put a 2 right here. Now I have 6 hydrogens, let's put a 3 right there. And we should have a balanced equation. What stoichiometry says is I have now a 1 mole to 3 mole ratio of nitrogen to hydrogen. I have a 1 mole to 2 mole ratio of nitrogen to ammonia. I have a 3 to 2 ratio of hydrogen to ammonia. So the coefficients in front of each compound gives you the ratio of one thing to another. And again, I refer to making cookies because we often use the analogy of recipes for cookies might only tell you how to make 1 dozen cookies, but if you want to make 5 dozen cookies, you just multiply everything by 5. Sorry, if you're going from grams of A to grams of B, first thing you have to do is convert from your element A or compound A grams to moles, which is what I showed you earlier on this chapter of dealing with the periodic table. Secondly, use the mole relationship. That's the balanced equation of stoichiometry to go from moles of one thing, moles of A, to moles of B. Then finally, you convert from moles of B to grams. I should just have a B there, sorry. Here's the example we're going to give you. 209 grams of methanol combusts in air how much water vapor will be produced. So first off, we need a balanced chemical equation. And actually, we're going to change this to just be methane, not methanol. So to begin with, CH4 is methane, that's a gas, plus O2, oxygen. Products of combustion reaction are carbon dioxide and water. That's a gas as well. So I need to balance my equation. If I put a 2 in front of my O2 and a 2 in front of my H2O, the equation should be balanced. 1 carbon, 4 hydrogens, 4 hydrogens, 4 oxygens, 1, 2, 3, 4 oxygens there. So now write down what you started off with. 209 grams, and again we're going to call this methane instead of methanol for this one. My first step is to convert my grams into moles. So this is the molar mass part. 1 mole, look at the periodic table, it's 16.05 grams. Once again, if you're more comfortable with just waiting there, so be it. Otherwise, I do my second conversion right away. And if the problem asks for how much water vapor is produced, I have 2 of the H2Os for every 1 of the CH4. Now I would be into moles of water, because if I show you, grams is canceling out with the first step, CH4 is canceling out with the second step. I want to get to grams, so my last step is that there's 18.02 grams in 1 mole of water. Moles will now cancel out. I'll be left with grams of H2O. Type in your calculator, 209 divided by 16.05, multiply it by 2, multiply it by 18.02, 3 sig digs in the final answer. I get 469 grams of H2O. And again, sorry that it says methanol in this problem, but we were going to want to do methane instead, a more common molecule for us. Chem 1, we were able to do this. Chem 2, we introduced something called limiting reagent. Limiting reagent in the simplest form is what's used up first. Excess reagents are the reactant present in a greater than necessary amount. So once again, if we go back to the making cookies analogy, if you only had 4 eggs in your house and you had an entire bag of sugar, the 4 eggs determines how many cookies you can make, because you only have so much of that. A bag of sugar, you have leftovers of that. If you have leftover, that's the excess reagent. Again, the limiting reagent determines how much product you can make, because if it limits how much is used up, you can only make so much with that one. Here's a sample problem that we're going to do. It says, if 124 grams of aluminum reacts with 601 grams of iron 3 oxide solid in a single displacement reaction, how much aluminum oxide is formed, and then how much of the excess reagent is left over. This will require a lot of stoichiometry. So hopefully you have a fair amount of room. Let's start off with the balanced equation, where I have aluminum plus iron 3 oxide. Single displacement reaction, which we will go over later, is when the 2 metals in this place switch places. So now I have Al2O3 plus Fe. And according to the problem, these are all solids. Need to balance by putting a 2 in front of my aluminum and a 2 in front of my Fe. Typically, what you might see some students do is write down what they're given. 124 grams of the aluminum and 601 grams of the iron 3 oxide. The way you know that this is a limiting reagent problem and not just a normal stoich problem is I'm giving you the mass of both reactants. And if that's the case, the first thing you're going to do is start with the grams of one of them and convert it to the other. So if I started with 124 grams of Al, my first conversion is 1 mole over 26.98. That's the grams from the periodic table. My second step is that there's 1 Fe2O3 for every 2 Als. My last conversion is that there's 159.7 grams in 1 mole. If I do these 3 steps, I end up getting 367 grams of Fe2O3. What I tell students to do at this point is to stop and think about what this means. In this question, if I had 124 grams, it would react completely with 367 grams of iron 3 oxide. Do we have 367 grams of iron 3 oxide. Yeah, we do. And we have leftover, as a matter of fact, which means this is our excess reagent right here. This is what we have extra of. This is how much I needed. I have more than that. So limiting reagent is the Al. That's your first step. So the question said, how much aluminum oxide is formed? Once I've determined that this is my limiting reagent, now I know this is how much grams can determine the aluminum oxide. By the way, if I wanted to start with 601 grams of iron 3 oxide and convert that to aluminum, it still would have worked out. But now that I know my limiting reagent is the aluminum, I'm going to start with 124 grams of aluminum. I'm going to convert it to the aluminum oxide. First step, 1 mole over 26.98 grams. Second step is there's 1 of the Al2O3 for every 2 of the Al. Third step is 101.96. It's my grams in 1 mole. My final answer for how much aluminum could be made, aluminum oxide could be made, is 234 grams of Al2O3. Once again, what I did is I started with the grams of aluminum and I compared it to the other reactant. Once I did that, I knew that my aluminum limited the reaction. Start with that, solve for the product you need. I only answered the first question there of how much aluminum oxide is formed. The second question of how much excess reagent is left over, I need to do a little bit more of. Pretty simple though. If I start with 601 grams of iron 3 oxide, and in the reaction I use up 367 grams, I just subtract the two. Rules for sig dig say they both end in the ones, so my answer should end into ones. I get 234 grams of Fe2O3, which is left over. Easiest thing you can do is try to practice this to figure this out. But again, it's the idea if you're given the mass of both reactants, first figure out which one is limiting. Because if you just go off of the first one, you're not necessarily going to be correct each time. There's one more question to do with this, and that's on percent yield. Percent yield is an application of limiting reagent. Percent yield is taking the actual yield, so how much you were able to actually get experimentally, divided by the theoretical yield, which theoretical yield is typically what stoichiometry tells us we should get, and then multiply that by 100. Here is a very long problem that we are going to solve. And this is going to combine stoichiometry, the balancing of equations, limiting reagents, and then add to the end of it percent yield. It says calcium reacts with vanadium 5 oxide solid in a single displacement reaction. I suppose it should say if 154 grams of vanadium 5 oxide reacts with 196 grams of calcium, what is the percent yield if 80.3 grams of vanadium are obtained? So first off, 80.3 grams of vanadium are obtained. That is the actual yield. Now let's go and try to solve this entire problem for the last part for this chapter. Calcium plus vanadium 5 oxide would be V2O5. Both of these, by the way, are solids. If you don't know why calcium is a solid on the periodic table, it's black, which means it's solid at normal conditions. It's going to make vanadium solid. And then calcium oxide, CaO. Which is going to be a solid in this case. Now we have to balance everything out. To balance this equation, I end up having to put a 5 in front of my calcium, 5 in front of my calcium oxide because I had to balance out the 5 oxygens, and then a 2 in front of the vanadium. I am given 154 grams of the vanadium 5 oxide. I'm given 196 grams of the calcium. I'm going to start with the grams of calcium and solve for the grams of vanadium 5 oxide. That will help me determine which one is the limiting reagent. Once I'm done with that, then I will start with the limiting reagent and solve for how many grams of vanadium were obtained. That will be my theoretical yield. I can compare that to the actual yield in the problem. That will give me my percent yield. So, to start off with, 196 grams of calcium. 1 mole over 40.08 grams. Again, that's from the periodic table, the mass of calcium. The second step is what we refer to as stoichiometry. There's 1 of the V2O5 for 5 of the calciums. Last step is convert that to grams of vanadium 5 oxide, which is 181.88. And this will give me by grams of V2O5, which when I solved was 178 grams of V2O5. Do we have 178 grams of V2O5? No, we don't. We have 154 grams, which means the V2O5 limits the reaction. Because if 196 grams were to completely react, it would need 178 grams. We don't have that much. Calcium is our excess reagent. Our limiting reagent is the V2O5. Now that we know V2O5 is our limiting reagent, start with 154 grams of V2O5. Our first step is going to be to convert that to moles, which just like before is 1 mole over the 181.88 grams. Second step is get it to moles of what we want to find, which is the vanadium. There's 2 vanadiums for every 1 V2O5. The last step is now convert it into grams, which is 50.94 grams for every mole. Divide, multiply, multiply. I end up getting 86.3 grams of vanadium. If this was a limiting reagent problem, we'd be done. There's one final step to do. We need to take this, which is our theoretical, and our actual. 80.3 grams is our actual, divided by 86.3 grams, which is our theoretical, multiplied by 100, we get a percent yield of 93%. This is the end of this chapter on mass and conversions and chemical.